So we are now at the end of an extraordinary week, and I'm really overwhelmed. Would like to thank the Kavli Foundation, of course, and the Academy, the Norwegian Academy for Science and Letters, and NTNU for your extraordinary way you treated us and your hospitality. So now to my lecture. I thought it would be instructive that I have to summarize, as also Ralph Nuzo mentioned before. I think in my case it's about 46 years of research in this area. So I thought it would be instructive if I go with you through what happened to one monolayer. This is actually the first organosilane monolayer that I showed that it really makes a monolayer. So this would be the exciting life of a most boring monolayer, and you'll see why. So brief resume of the life of this monolayer. Name OTS monolayer, we'll see in a moment what is OTS. Date of birth, 1978. This is the date of birth of publication. I started working on this at the end of 75. Basic education, when I learned actually what the monolayer is. It was between 78 to 84. Then it existed in a routine existence between 84 and 99. And then it became quite boring. You'll see why. And there was the beginning of new life, about 2000. And today, I think it is the star performer. So, what is all this? This is the first paper I published. I was a postdoc, you can see. This is from the Max Planck Institute for Biophysical Chemistry in Göttingen, where I was a postdoc with the group of Professor Hans Kuhn, at that time the mecca of Langmuir-Blodgett monolayers. So I will need another hour to explain you what is Langmuir-Blodgett monolayers, but very briefly, these are monolayers that are, Langmuir received the Nobel Prize for making monolayers which are similar to what we are now making by self-assembly on solid surface. These are monolayers floating on water, together with Blodgett, his research partner. They were able to transfer them on solid surfaces and to build layer by layer structures. And this, in the early 60s and in the 70s, having heavily used with the hope of making devices like molecular electronics. And this group at Max Planck Institute for Biophysical Chemistry was a leading group in this area. And you can see the department here, it's listed in English, would be the Department of Molecular System Assembly. So the idea is to use molecules to build architecture. So Epaminondas Emmanuel Polymeropoulos was a colleague, a postdoc. He was working on charge transfer through Langmuir monolayers, and I started working on self-assembly. So it's a long story why I started there. I want to learn about Langmuir-Blodgett, but what I wanted to do with Langmuir-Blodgett could not be done. You can read this in my bio, which is online. And then we started with self-assembly monolayers, and these are examples of, this is our hero today, OTS, which is a long tail octadecyl hydrocarbon tail, and has a terminal silicon atom, and it can bind to a variety of surfaces. Here you'd see it on aluminum. It binds through bonds like silicon O aluminum. This is a very similar long tail fatty acid that would also bind to aluminum, make a self-assembled monolayer by a different chemistry. This is making a salt, it is carboxylate, and this is a perfluorinated monolayer in which all the hydrogens in the hydrocarbon are replaced by fluorine, and they also make a good monolayer. And we're looking at electric conduction through these monolayers that we call them adsorbed monolayer, to distinguish between them and Langmuir-Blodgett monolayers. And to our surprise, even in the first trials, it turned out that these monolayers are much better insulators. So the Langmuir-Blodgett was difficult to obtain more than about 50% of good samples. The rest were short circuits. And with these monolayers had more than 90%. And at that time, we just started playing with them. So this was published, as you can see, in 1978. So this is the date that I put for the birth of this monolayer. And here we actually, I published a series of papers. And for publication reasons, some were published before the other that should have been published before, because we had to fight with referees, you know. So when you start something new and you start fighting with referees, some referees are more harsh than the others. And depending where you submit the paper, maybe the first paper is published after the second paper, and this happens. So this is from the paper that was submitted in 1978, but was published only in 1980. This is because of the referees, as I told you. And this is the most cited paper in the Journal of American Chemical Society. And you see, this is the scheme chemisorption of N-octadecyl trichlorosilane. This is OTS. So you see, this is a rather complex process in which chemistry is combined with what we call self-assembly or adsorption on the surfaces, because the initial compound, which is a trichlorosilane, is not a polar molecule. In order to have adsorption, you need a surfactant must have a polar end and a non-polar end, in this case, a hydrocarbon tail. And the trichlorosilane dissolves well in organic solutions, but is not polar. But reacting with water, the chlorines are removed, and this is extremely water sensitive, and you obtain in situ the molecule in which the chlorine is replaced by hydroxyl group, silanols, and this molecule now can adsorb on surfaces and also can bind covalently by condensation reactions, where a molecule of water is liberated, and you may have silicon-O-silicon lateral bonds and silicon-O-silicon bonds to the surface. This is glass surface, and this is very important. You see, the silicon of the molecule is actually the same silicon as the silicon of the surface. So then you get a direct binding of something organic to the surface. But this is extremely complex process, because the water, this is very important word, where is the site of the hydrolysis? If you have too much water in solution, the hydrolysis will occur in solution, and then you may get polymerization of this material, and you get a mess. So you'll see that it's very important that the solution is dry, and the water is only a thin layer on the surface, given a clean hydrophilic surface. So this is the title of this paper, Organized Monolayer by Adsorption, and this is number one. I told you that I had a number of papers. Actually, there were 4 papers from that postdoctoral research. And this is formation and structure of oleophobic mixed monolayers on solid surfaces. Now, the key word here is oleophobic. What is oleophobic? We know hydrophobic is repellent of water. So these monolayers also repel oils. It means that the monolayer forms from an organic solution, which is an oil, but once the monolayer is formed, you can withdraw the substrate from the solution completely dry. And this ensures that no more material adsorbs on the surface after the formation of a well-defined monolayer. So this is a key feature for self-assembly of well-defined monolayer, because if the surface is not a non-stick surface, more material would stick to the surface, and you cannot get a well-defined monolayer. So after I discovered this, I discovered that it has been discovered before, which was which was, I was happy and I was, of course, unhappy. Happy because I was not sure if I'm stupid or not, so I'm not stupid. Somebody else discovered it. But of course, it would be better to be the first. Anyhow, this was discovered by the time I was 1 year old. In 1946, this is the first paper on oleophobic monolayers. So these are monolayers that are formed by, in the case of the group of William Zisman, they worked at NRL Naval Research Laboratory in Washington, D.C. These monolayers, they investigate monolayers that form on metals of long-chain fatty acids, and they coined this term oleophobic monolayers. So again, you see what is the key feature here. You have these molecules floating in solution. This is the active ingredient. The solution is an organic solution. And once the monolayer forms, you get a well-defined droplet. It means the liquid doesn't stick, and these molecules do not stick, so you end up with a well-defined monolayer. What the research that has been done, starting with this work, the first work was this one, it was in the 50s and also in the 60s, was focused on wetting properties to learn a lot of work on wetting, and on lubrication, and on friction. This is lubrication, of course. And by the way, this is the mechanism of lubrication in engines. You have in engines an oil, but the lubrication is not by the oil. The lubrication is by the monolayer that forms from molecules that are in the oil on the metal parts. So while there is wearing during metal parts moving one on top of that, the monolayer reforms itself by self-assembly. So this is what they were doing, and my idea was to use this in order to build on the surface. This is what we are now talking about, nanofabrication. Okay, this is William Zisman. And this is just a brief view of what is the mechanism of formation of good OTS monolayers. You have to start with the hydrophilic. In this case, I show silicon. Silicon has always a native oxides on the surface. You have silicon OH. Like on glass, you may have this also on metal. So there are a large variety of different surfaces which have this feature on the surface, OH groups. And if the solid is clean, and this is another problem, how to clean it and to keep it clean, then you will always have a thin layer of water, which may be a monolayer or several monolayers of water on the surface. Then you bring it in contact with this solution, a dry solution of these octadecyl trichlorocyanate molecules, and then the entire assembly and chemistry occurs at the surface. So the chlorine are removed, hydrochloric acid is released, the silanols can condensate, and they may form bonds to the surface, covalent bonds and also lateral bonds. I should stress not each molecule has to bind to the surface, and this is very important. Actually, there is a lot of mobility here, and this is also a very important feature of these monolayers. This has to be distinguished, for example, for monolayers of the kind that we have just heard before, like thiols on gold, or the binding is to specific atoms on gold. Here we do not hear a specific binding, so the monolayer is like more or less like a Langmuir monolayer. This is a Langmuir monolayer floating on water. So our monolayers, these organosilane monolayers, are formed on a very thin layer of water on the surface. So in this sense, they are similar to Langmuir monolayers. So there is a lot of lateral mobility. This, you can see this is a model where you see these are the hydrocarbon tails that packed together by van der Waals forces, and the silane head groups, the hydrolyzed silane head groups, can bind laterally, and there is a lot of dynamic equilibration. It means bonds can form and bonds can break. This is like a water molecule moving around. So when a water molecule is taken away, a bond is formed. When a water molecule is incorporated, this is hydrolysis, the bonds are broken. So this gives a lot of mobility, which is necessary for creating a self-healing process in which you get the perfect structure. This is very important. Okay. So this, to summarize to this point, these are the unique, desirable properties of alkyl trichlorocyanate monolayers, compatible with a large variety of polar surfaces owing to their mode of formation and bonding, self-healing of structural defense owing to the high mobility and dynamic equilibration of both intermolecular and molecule-to-surface bonds, high structural perfection resulting from the self-healing of structural defects, and exceptional chemical thermal and electrical robustness owing to the formation of both vertical and lateral covalent bonds and the chemical inertness of the non-stick monolayer surface. So these are very important properties. This is an example of using this property, which is inertness, oleophobicity, non-stick properties. And this is one of the papers that was published in 1979. It was supposed to be the third in the series. So it was published before the first. Okay? Because to publish in Israel Journal of Chemistry took less time than the Journal of American Chemical Society. And of course, this paper was not read at that time by many. We didn't have at that time internet and Google. And what was done here, this is a mixed monolayer. We have OTS together with a long-tail dye. The dye can be dissolved from the surface. The OTS monolayer sticks to the surface and cannot be removed. So it was possible to create molecular holes that have a memory of the shape of the dye molecules. And then dye molecules can be reabsorbed in those holes, since the dye would not stick to the outer surface, only into the holes. And if you have a dye that fits into the holes, it would absorb. If you have a dye that has a shape which is bigger than the hole, it would not go into the hole. So this led us to create surfaces that exhibit memory effects, and we call them skeletonized silane monolayers, because you start with a mixed monolayer, you create here a skeleton monolayer with the holes that preserve the memory of those molecules that are taken away. Now, coming back to the excellent properties of this layer, the OTS, it turned out to be an excellent ultra-thin insulator, a tunneling barrier. And this has been used. So now I am jumped to 2012. So you see, the hero here is graphene. But graphene should be placed on something inert. And OTS was used in this paper. You can see that we have graphene on OTS, and you see what is written here: transport, magnetotransfer of high-performance graphene transistors on organic molecule functionalized substrates. But here the OTS is not the hero. The hero is graphene. But OTS helps. We very much wanted that our monolayers are the heroes. So in this sense, the OTS helps. It can be useful, but it's not the hero of the story. Okay, so I told you that what I had in mind when I started with this, by analogy with language blowjet monolayers, to be able to build away from the surface. The surface be just the site which enables us to get molecules organized. So for this, in order to do molecular architecture, what was necessary in order to build what we thought should be functional molecular assemblies? We should have control on the vertical dimension. It is layer by layer self-assembly, like in the language blowjet, and also lateral control, which can be achieved by patterning. And what can we do with the OTS? The surface is inert, non-stick, unsuitable for further manipulation. You end up with a single monolayer. We cannot put more monolayers. This is the desirable property of self-assembly. If more material will stick to the surface, it will not be a monolayer. But on the other hand, that's the end of the story. So we are at the end. So what next? So at that point, OTS becomes a boring material. So we need still a non-stick oleophobic surface, but not chemically inert like OTS. What does it mean inert? You cannot, by chemical methods, convert the top surface, which is CH3, to something that would be active. It means like a hydroxyl or a carboxyl, because to do this, you will destroy the monomer. You need so harsh conditions that it is not possible to achieve this. So OTS is unsuitable. It becomes a most boring monolayer. And this is the solution to which I arrived. But this is, you'll see what happens with this solution. So instead of OTS, which is terminated with a CH3 group, we synthesized a molecule, and this is totally new now, which is also a long hydrocarbon chain, but has a terminal double bond, CC double bond, which is now reactive. Now, and it can be reacted on the surface and convert the double bond to a hydroxyl group, and now this becomes an active surface to which you can bind the next monolayer, like the monolayer that binds to the hydroxyls on the glass surface or on the silicon. Now, this was a kind of suicide project in terms of risks that one takes. And I was quite irresponsible because this was also the master thesis of a student. And I was a new hired scientist at that time. Why it was a sort of suicide project? First of all, we had to synthesize a new material and to make sure that we make it. Then we didn't know if this material will make a self-assembled monolayer, so we had to check it. Third, it is the first time that a chemical reaction was done on a monolayer, and we had no idea if it is possible, what it will be the yield, and whether the monolayer will resist. It will not be destroyed, or the structure will not be destroyed. And second, who tells us that it's possible to put another monolayer on this? So each step in this project would be the end of the project if it doesn't succeed. Looking back, I think that I was quite irresponsible to take a student to do a master thesis on this, but probably I strongly believe that it works, and it works. So this is the paper that we submitted in August 1982, and was published, appeared in the 1st of February 1983, and you see the title is A New Approach to Construction of Artificial Monolayer Assemblies, new compared to Langmuir-Blodgett. And if you read here, we are talking about assembling of artificial layer structure based on self-association and self-organization of molecules occurring spontaneously at solid-fluid interfaces. The term self-assembling monolayer doesn't appear here. You see, we have assembling, we have self-association, self-organization, but not the exact term self-assembling monolayer. Why? So this was published in February 83, and in April 83, our public relations department at the Weizmann Institute sent me this note. Look what they write in New Scientist. This was a report on our paper. So this report is 7th of April, 1983, in New Scientist. And the title is, I don't know who is the author until these days. So the title reads, Monolayer fields that assemble themselves. This is taken from our paper, and here you see self-assembling monolayer fields. So this is the origin of the term self-assembling monolayers. Later that year, we published the first paper using this term. So, you see, this was submitted in November 1983. The title on the formation and structure of self-assembling monolayers 1. There was a series, and this is part of Rivka Mo's PhD thesis. Rivka is sitting here. We have been partners since 1980, when she being the first PhD student receiving a doctorate in this area of self-assembling monolayers. And you see that nobody knew what is self-assembling monolayers, so now there is a subtitle explaining the title. It reads a comparative, and this is study of Langmuir blotted and adsorbed films, adsorbed, this is self-assembling, on flat substrates and glass microbeads. This paper is 30 pages. Today it's not possible to publish something like this. We have here monolayers on silicon, zinc selenide, glass, germanium, fatty acids, and silanes. So I have not mentioned previously that that we also invented here the methods of characterization. When we start making monolayers and multilayers, how do you know what you have here? So we used actually for the first time infrared spectroscopy in a quantitative manner, in a different way that Dave Alara developed it. We heard from the previous lecture. We actually compared how it was, we characterized our monolayers by direct comparison with Langmuir monolayers that were known and have well-defined structure. So the infrared was applied to our self-assembled monolayers in parallel with Langmuir monolayers. So they were the standard versus which we could decide what structures we have on our surfaces. Now, with this approach, we could really build. And what was another discovery, that actually we don't need covalent bonds between layer to layer. It is possible to create multilayers in which the lateral bonding is sufficient and the bonding between the layers is not covalent, is hydrogen bonding. And once we have such a, what we call it, a free multilayer matrix, in one step, it turned out to be possible to intercalate ions and other molecules. And this is something extraordinary because this structure is non-centrosymmetric. At that time, there was high interest in making structures that exhibit the phenomenon of second harmonic generation. For second harmonic generation, we need a non-centrosymmetric structure. With Langmuir blotted, you obtain always centrosymmetric structures. I mean, you have the polar interfaces are centrosymmetric. Here, inherently, we have non-centrosymmetric. Here we have a layer of carboxylic acid groups, and we have a layer of silanol groups. So this forces this molecule, which is a polar molecule, to orient itself automatically with the amine toward the carboxylic acid and with the carboxylate toward the silanol. So this indeed exhibited the property that we expected. And this is the paper published in 1995. You see the title is Third Layer Self-Assembly. What is third layer self-assembly? We assemble a monolayer, first level. We assemble a multi-layer level, second layer, and then we have intercalation in between the layers. So it's third layer self-assembly and beyond, because you can then modify what is inside. And polar hybrid superlattices via post-assembly intercalation through non-centrosymmetric multi-layer matrices of hydrogen-bonded silanes. So this opens a lot of possibilities. Unfortunately, not many groups followed it, probably because it was much easier to stay at the ground level and work on monolayers only. So, this is the end of these molecules with the terminal double bond, which are actually difficult to synthesize and makes everything expensive and unavailable to most those that want to work with such layers, because most those interested in such structures are not chemists or organic chemists and don't know how to make these molecules. And indeed, to make good molecules with a terminal double bond is not easy. So now we are in 2000 is the comeback of OTS. And this is due to the possibility of surface functionalization of inert monolayers. Okay, so this is the invention of what we call constructive nanolithography. Again, Rivka, she's over there. She had the idea that we should be able to do something with this boring monolayer, with OTS. How can we functionalize its inert surface? And at that time, you know, when I started with the monolayer, it was long before the invention of the FM, but in 2000, actually this work started in 98, the AFM was already available. And the idea was that if you take AFM with the conductive tip and apply a bias, it should, I mean, this was Rivka's original idea, it should be possible, perhaps, to create a small spark in the air, and that will somehow affect the stove surface. And she tried this together with Sidney Cohen, who is our expert in AFM. Eli Friedman was a PhD student at the time, and it worked. It turned out that the mechanism is different. It's not what Rivka thought, but it works. The mechanism is actually electrochemistry. A small droplet of water condenses by capillary condensation in air if you have sufficient humidity on the tip, and everything is now electrochemical patterning. So everything is in a small nano droplet of water, and here we can locally convert CH3 to carboxylic acid quantitatively. How to prove this, I need another lecture to show you, but again, quantitative infrared spectroscopy and other things. Now we have also AFM as a tool. And we can build only here, and we can have a step, and we can measure the height, and so on. So this is, again, a unique type of lithography. We heard about a lot of lithography. Most lithographic methods in the area of monomer are done two ways. Either we place molecules on the surface, like in soft lithography, and then you have to fill in the surface with other molecules, or you start with a complete monolayer, you destroy it locally. You can do it with an AFM tip with high force, or other means, or with an electron beam, and then place molecules of interest in that place. Now, both methods are very useful for many applications, particularly in biology, but not in electrical applications. Then we'll see why. Because this is the only method that doesn't create any defect at the interface between functionalized and non-functionalized. The structure is totally preserved. You only convert CH3 to carboxylic acid. And this is very important because if you then we have to place electrodes here, if you have a defect, you have leakage. And it's no longer possible to use it for any electrical applications. So, just a moment. We have now carboxylic acid. They are densely packed. And we also found with infrared spectroscopy that we have lateral hydrogen bonds. Now, from our previous work, we knew that we can intercalate ions here. The intercalation involves replacing protons with ions, different ions, in this case copper ions. It means you start with free carboxylic acid, you end with copper carboxylate. This is a process which is triggered, controlled by a gradient of chemical potential gradient. You actually place a slide coated with these multilayers, and then the ions move with extremely high speed, unusual speed, because it's not just diffusion. They are driven and replace protons. So we know that we can have extremely fast ionic motion. And then the idea came that perhaps we can do this. We can pattern our OTS monolayer, place electrodes, apply a bias, and eventually see whether we can replace proton and move ions laterally. And this idea was that we are going to make ionic circuits, nanocircuits. So you know, in the living organism, most of the electrical events are not electronic, are ionic. But nobody did anything artificial where you can move ions in a controlled manner on a surface. So the idea was to make circuits, and we could pattern with the FM tip. Then we developed the possibility to pattern with stamps, so actually with electrical stamps. So actually it was possible to make macro channel structure, to make micro, and to combine them. It means you can do anything you want in this way, and the ions should move. And in 2015, we actually published this, single-layer ionic conduction or carboxyl terminated silane monolayers patterned by constructive lithography. And with infrared spectroscopy, we could show directly the patterning process. You see this, in this region you are looking at the CH stretchings. And this is the methyl And if this is the original OTS, there is nothing here. After the patterning, this disappears quantitatively because the metal is converted to carboxylic acid, and this is the carboxylic acid features. When you start applying bias, this disappears, and this feature appears, which is silver carboxylate. So we can see directly that we replace protons, and this is a lateral process. There is no liquid here. Everything is in vacuum or under inert atmosphere. So a dry process in which you apply electrodes, and this is, and this works very nicely. Now I jump further. Okay, I have to jump fast. So what I've shown was done with patterning with an AFM tip or with a stamp for which we need water. You remember the droplet that condensates on the tip. Now this makes problems because if you want to move fast and you apply a bias, sometimes this water evaporates and then there is a break in the line that you want to make. So it is unstable. So we were looking for something else, but we didn't know exactly how to do it. And here again, serendipity comes in to help. And this is a process that was discovered, and I have no time to tell you how it was discovered because it's interesting. But what was discovered is that if you place, what you see here, we have silicon wafer, here we have the OTS monomer, on top we have a thin layer of polyvinyl alcohol. Polyvinyl alcohol, I think it's a polymer that contains OH groups. And it's very popular in many applications, also in cosmetics and so on. So it turned out that if you have this sandwich and we irradiate it with either X-rays of electrons or UV at short enough wavelength, or you place a similar OTS monomer, which is an electric stamp, and apply a bias, both work equally. It is again possible to convert the CH3 to carboxylic acid while preserving the structure of the monomer. This is extraordinary because here we don't need any longer a liquid. The PVA is perfectly stable. So the PVA now provides the oxygen needed for this reaction instead of water. It's absolutely exactly the same. And as it turned out, probably when we say X-ray and UV, we are talking again about electrons, because X-ray extract electrons from the surface. In this case, you can use electrons with different energies. Here in the stamp, we are talking about something like 10 volts that you apply, and it works as well as high energy electrons or X-rays. And this is what we refer to as interfacial solid phase chemistry. This is again a discovery. So I'm going through a chain of discoveries and inventions. You know, you discover something on this basis, you can invent something on the other way around. And so actually what I wish to emphasize that if you have an open mind, the results of your research drive the research. I mean, from the results that you get, you have the idea for the next step, provided that you start with something that makes sense. Okay. So once we knew that this can happen, and okay, this was published in Angewandte Chemie, you can see it, and on this basis, we invented what we refer to as interfacial electron beam lithography. We are now in 2018. So this is exactly the same process now on the nanoscale. We can use the electron beam of an electron beam writer, which is used in electron beam lithography with resist, but in a different way. So here, the polymer is not a resist. It's a reagent and a catalyst. So we write with the electron beam, the reaction occurs at the interface. Then it was found that you don't need, I mean, you can use different polymers. You can get different reactions. Actually, you can even use a thin film of metal that contains oxygen. I mean, if you evaporate a thin film of silver, bring it into the air, it gets oxidized, and it can also release oxygen. So you can write on this, you can write on this one with the beam. You remove the PVA or the metal, and then you have a pattern we refer OTS oxidized. There's no other name for this because you don't have this compound anywhere except on the surface. And then you can write anything you want with the electron beam. Now this is, since the electron beam machines are perfected for patterning, while the AFMs are produced mainly for imaging, the capabilities that you have for writing with electron beams are much more developed than with the AFM. The AFM is limited to a scan usually of the order of 100 micrometers. You'll see that with the electron beams you can write centimeters. So this is the paper that we published on interfacial electron beam lithography, chemical monolayer nanopatterning via electron beam-induced interfacial solid phase oxidation. And I should mention that 3 of the first authors, Rivka here, Jonathan and Doron, participated in the events in Oslo this week. So to give credit to the people. And you see, with this we can now do a lot. This is the logo of the Weizmann Institute, written on top of this monolayer with different electron doses. What you see here are lateral force images. There is no height difference here. Between the carboxylic acid and the metal is very little difference in height. And this is a topographic image. There is nothing. You can see this only in lateral force, which measures friction, because these are different materials. So if you go with the scan in this direction, you get this contrast. If you go back, you get the opposite contrast. So as Professor Umar said, is this bright or depending how you take it, because what you measure is the bending of the tip. And this is a phase image in tapping mode, which shows that we have different materials, different sticking, and different elasticity. But there is no topography. This is important. If you use too much electrons, I mean, higher doses will eventually destroy everything, and you get a topographic image as well. Okay, we can do anything we want. We can make lines, we can make dots, different widths, and we can go to about 10 nanometers according to AFM. Maybe that we have better resolution, but the AFM now competes with the electron beam, which is which in the resolution. Okay, so too fast. So now we place 2 electrodes, in this case silver electrodes, and apply a voltage bias, and we know that what we expect, and we expect that ions will move. So you have lateral electrochemistry, but they are doing more. So now we have additional surprises. So ions indeed move, but then when a silver ion arrives at the negative electron, it gets an electron gets an electron, is reduced. And then instantaneously, a silver filament builds from the cathode toward the anode, and we create now a nanowire of silver automatically, and this is a very fast process, and then the electronic transport takes over. So you have without the lateral ionic transport, this would not happen. But then we have a laterally grown metal nanowire, and now the action starts. So this is another picture of what we have here. You see these are the silver electrons. This is the line written with what we call it an ionic channel, with the nano channel with the electron beam. The ions move while we apply a bias. And then how we analyze this? The first is to look at AFM. So you see immediately that we have metal here. This is an AFM image, really AFM image, of a length of this channel between these 2 electrodes. This is the cathode, the anode, and this is about 26.5 micrometers. And if you take a cross-section, you have something of the order of 1 nanometer of silver. And this is a limiting height. It doesn't grow. It doesn't matter how long you pass current, probably because when the electronic conduction takes over, no more ions accumulate and are reduced. So this is very important. Now, this is how such a device looks like. I mean, this is the cartoon, and this is an optical image taken from the top. This is a piece of silicon wafer coated with the OTS monolayer. The line is written with the electron beam along this line between two scratches, okay? What you see here in yellow is just to show where it is. And then we evaporate 2 silver electrons. And in order to make soft electrical contacts, so we don't go through the monolayer, we use polyvinyl pads, and the electrodes are evaporated on top. So now when you touch here with the probe, it doesn't go into the monolayer. This is also important. So there are small details that if they are not processed well, you don't get anything. So, you know, the secret is in the small details. Now, this is the image of the line that you cannot see here, but this is an AFM image of a portion of the line. And now, with the electron beam, we can write extremely long lines, and without the problems that we encounter with the AFM and the water and so on. So here you see, so this is when you see IBL's interfacial electron beam lithography. This is a line of 2 millimeters with a width of about 20 nanometers. And you see here the cross-section. And these are just markers in order to find the line on the surface. Now, to have an idea what it is like a highway with a width of 20 meters and a length of 2,000 kilometers. And with AFM, what we see here is about 60 micrometers, and if you want to go to higher resolution, we have only 5 micrometers. So how do you know what is the quality of this highway? Is this a good highway or not? With AFM, there is no way to find it out. The only way is to measure electrical properties, because if the highway is broken somewhere, we'll have no conduction. Okay, this is another, we can do any shape. So this is total length 2 millimeter, and the width here is of the order of 12 nanometer according to FM. This is also a very good conductor. Okay, so now what we are doing, we are placing electrodes, and we can place electrodes at different distances from one another. And we can also, what is interesting, these are extremely robust structures. We can remove the electrodes by dissolving them in strong gases, strong nitric acid, and place new electrons on the same wire at different distances and see what happens. And here you see that we have the resistance. We just measure the resistance by applying a voltage of 1 millivolt and versus the length of the wire divided by the width. So this is resistance normalized by the length and the width. And the result, I mean, from the slope, what is obtained is what is called sheet resistance. But this gives you a measure of how good these conductors are. Now, you see 2 curves here. And now is the next surprise. The conduction depends on the silicon. If you take N-type silicon or P-type silicon. So, an N-type silicon, they are poor conductors. On N-type. On P-type silicons are good conductors. This is with low doping, and this is with higher doping. It's a factor of more than 3. This is better conductor on the highly doped silicon. It means silicon that has more holes than this one. But you see, these are these are perfect lines. So it means that the thickness must be the same along the line, because we divide by the length divided by the width, but the sheet resistance depends on the thickness as well. So these all must have the same thickness. Then, furthermore, we said, let's see what happens if we pattern only as a function of the length. If we pattern only as a function of the length and take all those dots that are on the line, it turns out that all of them have the same width by AFM, which in this case, on the low doped and the high resistance, high resistivity P silicon is about 50 nanometers according to AFM, and to the other one is about 20 nanometers. So all these must be uniform. But if you look at AFM, they don't look so uniform. So the electrical measurements show us much more than the AFM shows. So something, so how good is the conduction? So how good the conduction, if we compare it, assuming that the conduction is due to the silver, which is formed on the surface, we compare it with the bulk silver. So it turns out that this is much better than bulk silver. In the case of this line, it is about 14 times better than silver. In this case, it's almost 48 times better than silver, bulk silver, if you compare the resistivity. I have not mentioned the thickness I mentioned already before, it's about 1 nanometer. We know the width, we know the length, and we know the thickness. So these are much better conductors. If you look at the FM, they look grainy. So the conduction should be poorer, but the conduction is much better. And even if you compare it with graphene, you see that this is much better. So now we have a series of surprises. It depends on each substrate you put it. There are more data that it depends also on what you put on top of it. If you cover it, depending on what you cover it, the resistance changes. And then we said, okay, this silver is formed by, at the moment we applied the bias, by the local electrochemistry, but we wanted to put silver that we know it's silver. So how are we going to do this? Oh, so this is a new invention, it works. So now we have interfacial electron beam in lithography at 2 interfaces. We have here a sandwich, we have silicon wafer, we have the OTS monolayer, we have a thin layer of PVA. On top of this, we have a thin layer of evaporated silver. So that's the silver that we evaporate, we know it's silver, okay? And now we write with the electron beam, and then we peel off. Now, here is the good property of OTS non-stick surface. So everything, I mean, the PVA doesn't stick well. And the silver is evaporated on top of the PVA. So something remains on the surface only where the electron beam was used to write the pattern. And what is left of the surface is now PVA that sticks. So now we have a reaction at the interface between PVA and OTS, and between the silver and the PVA. So now we have silver on PVA on OTS. It's no longer OTS because something changed there. And this is the only way that we can make now, we call them composite nanowires, because we have now silver and we have also the PVA. We can evaporate, we can remove the silver chemically and see what happens underneath. So there is a lot of work going on. And this is now ongoing on. What I'm telling you now is unpublished results, okay? So actually, it will be nice to hear from the audience what is your impression about all this, because we do not understand everything. And this work is now done by Rivka Maoz and Aruf Sarkar. He's a postdoc working with us. So what is the finding here? So now these are much, much better conductors with the PVA, silver on the PVA. So if we use the same measurement with 2 probes as before, now we are down. What I've shown before are kiloohms on the scale and hundreds of ohms. Here, on lengths of hundreds of micrometers, we may have 20 ohms or so on. But if we use so-called 4-probe measurements in which we get rid of contact resistances, now we are down to what appears to be nothing, less than 1 ohm. So what is this? So this is extraordinary conduction. Even if we make calculation, is 5 orders of magnitude at least higher than bulk silver. If we take into account, and you see what is the size? We have to decide what is the size using AFM. But AFM doesn't tell us the entire story. And what the AFM shows is the following. We have such a composite nanowire that has a height, this is the average of this segment, of less than 1 nanometer. This contains both PVA and silver. We don't know yet what is the thickness of the silver and what is that of PVA, because this is underway, this research. But of course, it's very, very, very little. We believe that we are talking about a single layer of silver, just like graphene, a single layer of silver. And the width is about 50 nanometers. And it is an exceptional conductor. So, looking in the literature, you find the following. What may be? We are now talking about theories of high-temperature superconductivity that were proposed in the late 60s, the early 70s. This one was by Little at Stanford. He was talking about a one-dimensional conductor, which would be, as a one-dimensional metal, this could be implemented according to what he proposed as a molecule, a conducting polymer molecule. And the mechanism proposed is not the usual mechanism of superconductivity induced by phonons, by coupling of electrons through phonons, but the so-called exciton mechanism. So he proposed that if you bind to this one-dimensional conductor polarizable molecules, but separated from the conducting line at small distance, so that there is no electrical cross between the two, then the electrons flowing here repel electrons in these groups, and then positive charges attract the next electron. And this is the proposed, in a simplified manner, the proposed mechanism of coupling between electrons to make the copper pairs along the one-dimensional metal. And the similar theory proposed by Ginsburg is to use a two-dimensional metal with a thickness of not more than 1 nanometer between, let's say, two semiconducting materials that provide this same mechanism of exciton coupling. So now we start thinking what we have is exactly or very similar to this. We have something that is between one-dimensional and two-dimensional. By the way, the high conductivity is only on the nanoscale. If we make them much wider and much more silver, then become regular conductors with conductivity poorer than the bulk silver. So that's the point. Of course, we have to do all these control experiments. And then there is even, but you remember that our conduction is enhanced on p-type silicon and depends on the doping. It means the more holes, the better the conduction. So now we come to this paper published by in Soviet Union in 1976, a new mechanism of superconductivity, pairing between spatially separated electrons and holes. And if you look at, and also predicting high temperature superconductivity, and here you must have an electron and a hole moving together, separated by thin insulator that prevents tunneling between the two. So what we have on the silicon, a thin layer of silicon oxide, about 1 to 2 nanometers, our monolayer, about 2.6 nanometers. On top, we have silver, and underneath, we have holes. So it also looks like this, although in our case, we have much more surprising results, which are not predicted by the theory. So now I think I come to the end of this lecture. So this is the end of my story today. Interfacial electron beam lithography pattern OTS monolayers are about to reveal the secrets of high temperature superconductivity. This is the quite exciting performance of a most boring monolayer, if it is true. In any case, I mean, I'm not declaring here, and don't cite me that I claim to have room temperature superconductivity, but we have something exceptional in terms of conductivity. Hopefully, it is. For this, we now collaborate with a top group experts in superconductivity at our institute in condensed matter physics. We are chemists. If we claim superconductivity, nobody will believe us. physicists, experts in superconductors, and there are many more measurements, of course, to be done to find out what it is. Eventually, if it is, next time we are in the other country. Thank you very much. Very good question. Underway, there are intriguing results. Intriguing results. This is what Rivka is doing right now. There is interaction. There is. But I cannot summarize the results. They are underway, but they are intriguing. Okay? So I told you there are many, many things here that surprising. So every time we do something, something else comes out of it, not what was planned. And this is the fun, or no?
So I must admit, I was a little confused. So when your devices, I thought you said that your conduction was ionic.
Yeah. It was, no, okay. If we look on the macro scale where we measure the infrared, unfortunately we cannot use the infrared on the nanoscale. You know why? There are now nanoscale infrared, but we don't have money to buy. Okay? But if we look on the macro scale, we actually see the ions moving. And the ions are necessary to make the wires. Not the last ones, we just put the silver there. I mean, if we reduce the carboxylic acid to alcohol, insulator. If we chemically now convert back the alcohol to carboxylic acid, it is high conduction. So without the ionic conduction, we do not get the electronic conduction. So it's a complex system in which we have both. Now, on the macro scale, the conduction, if we compare, I mean, if we normalize the width and the length, it's about 3 orders of magnitude less. So I guess that on the macro scale, we may have some filaments, but it's not macro scale. I mean that we have centimeters wide. Okay? So mostly we have ionic, but maybe also some electronic, but not. But on the nanoscale, when we go down to these channels, which are tens of nanometer, it's probably electronic, but we need the ionic to.
Of course. Yeah.
And also in this last system where we put the silver, we don't know yet exactly what is the ionic part, because we know already that in the PVA we create carboxylic acid groups through this interfacial oxidation. Okay?
Yes.
So we don't know exactly what is going on. I say it's underway.
Yes.
It's known from other systems that transport properties are size dependent. For instance, diffusion coefficient. Depending on the porous media they are in, it varies with the length, say, of the characteristic length. So would you think that is interesting to vary the diameter of the...
This is what I've shown. We had length divided by width. But this was on the nanoscale. If we go to the micro scale, much poorer conduction. I mean, if we make them bigger, they are poorer conductors. That's the point.
So does it scale with one over the length?
To a certain, here I've shown that it's proportional to the length, but depending what is the width. I mean, if we go to macro scale, let's say, if we make centimeters wide, they are poorer conductors. The width, the thickness is less under control. This depends on how the lithography is done, and we peel out, I mean, we remove most of the silver, it is removed. What is left that sticks to the surface is also a few nanometers. But if we we can make them by other means that are wider and with more silver, okay, by just evaporating the silver. And these are poor conductors. So it's certainly an interfacial effect. That's why I'm talking about those papers that predict unusual conduction interfaces by either the exciton or by pairing of electrons and holes across the interface. It's not that the material itself, the silver itself is silver, no. It cannot do it. It's only the structure itself, and this is a nanostructure, and the interface is important. So this is where the entire story is about monolayers here, you know. So it's not that we don't make a material, we make a structure at an interface. And this gives the unusual properties.
Yes.
Just one more question. I mean, when you go almost to atomic layers of your silver, of course, then your band structure is very different to that of your macroscopic thick layer. So, it's hard to believe that you have really a continuous band of silver, but more atomic silver with.
So they say, if I look at the FM, I would say that this should be a poor conductor.
Yeah.
Okay, but it's very good conductor.
Okay.
So an atomic layer of silver we cannot see with the FM. Yeah. In any case, if you have more silver, what we see is what we have on top of that. But must be continuous. Okay, we have a lot of control experiments here, of course. So one thing is to make not a continuous line, but a broken line with gaps between segments. Now, if the gap between segments is more than 30 nanometers, is insulating. If we start closing the gap below 30 nanometers, it starts conducting. This is probably the resolution of our lithography, okay? So this is a way actually to check what is going on. And then a 25 nanometer, a nominal 25 nanometer gap is a perfect conductor. But of course, if it is not continuous, it doesn't conduct. Of course, we have to check, we have leakages and all this, I told you. So one way to check is this, to make the same line, but not a continuous one, insulating.
So this Russian paper that you found, that's that's theory, that has the spatially separated charges, right?
Yeah.
So considering how many people are working on single electron type devices, it's hard to believe that people haven't tried to.
No, they
cited that?
Yes, but they could prove that there is coupling, but they didn't find superconductivity.
Okay.
The systems were not. You see, the problem, also the exciton mechanism.
Yeah.
There were many attempts.
Yeah.
But the physicists work with physical methods. And with those methods, it was not possible to realize a system that has the predicted properties. We arrived at this indirectly, you know, but we have the ingredients that came in. Actually, right from the beginning, I thought about superconductivity, but in a totally different way, not like this way. Okay. Also by accident. So we have the right system, you know, the insulator with the right thickness, and apparently, but I say, even if it is related to this theory, the theory doesn't predict many of the phenomena that we observe. So, for example, if we make the same ionic motion at the interface of a bilayer, we can make a bilayer. Mm-hmm. The conduction is much higher. But why what is on top of this is just an OTS monolayer influences the conduction? Also, we don't know.
Yes.
I was wondering if you've tried it with other metals.
Excuse me?
You might have mentioned this, but have you tried it with other metals?
In the paper that I cited from Nature Materials, we are showing that a number of metals release ions that move, unusual. For example, aluminum, titanium, all move on the surface, and we can see them. But the electrical measurements, we tried only with silver. You know why? I have a group of 2-3 people. There are many metals. For each metal, I need at least to another one. So I have to decide what to do.
Yeah.
But so it's not clear if it's something with silver or...
There are many, you know, there are so many questions. For this, I would need a group of 40 people. Each one will do something else, and provided that each one knows exactly what to do. Because this is something new. You don't get people trained in this. These are our inventions, you know. And a postdoc, to start doing useful work, we train the postdoc for at least half a year before we have something and we are not sure if it is true. You know, there are many ways to go wrong here. We are all the time in what is called terra incognita. We don't know what to expect, and actually the research is driving us, provided that that is correct.
Very good. So do we have any more questions? This has been really great. We've gone from Kavli Prize to Gordon Conference all in the same afternoon. It's fabulous. Thank you so much. Let's thank Yaakov again.